first talk for the day is Capturing Mask ROM by John McMaster. I do call him a hidden gem in the hardware security space. And if you all ever get to meet him, definitely buy him a hot chocolate so that he's much more motivated to show you his fancy lab in the garage. I have a small picture of John from last year where he was in his lab coat presenting the talk. And I hope he keeps the trend of wearing a costume for his talk today as well. John, the stage is yours.
Can you still hear me?
Yes.
Should I do the whole presentation like this?
If you don't want to catch coronavirus, then yes.
Well, I do also want to breathe, so I will take it off now.
Yeah.
Okay, if that's all good, then I will get started.
Go ahead, John.
All right. Well, thank you, everyone, and welcome to hardwear.io Virtual 2020. My name is John McMaster, and I'm going to talk about capturing mask ROMs. So, without further ado, what is a mask ROM? Basically, when you have a microchip, you might need to hard code some firmware or other data onto the chip. Sometimes maybe it's the boot ROM, that's going to boot off of flash afterwards, or maybe it's the actual main program data. And the reason why you might do this is because versus flash, it's faster, it costs less, but the biggest disadvantage is it's actually part of the chip design. So when you actually fabricate the chip, polish down the layers, do all these chemical processes, you are physically encoding that data onto the chip. And so this talk is going to talk about how to look at that physical data and extract it from those chips so you can get that firmware or whatnot. And the reason why you'd want to do this is it could be that you want to analyze the boot security. So I mentioned maybe there's a bootloader, maybe it checks signing on the chip and you want to know, hey, how did this chip do the signing check? Maybe it has a problem in it. And if I do that, maybe I can get code execution on a chip that I wasn't supposed to. It also could be that sometimes there are old machines that have these mask ROM parts, say for example, a very large lathe, and maybe they had a noisy power supply that was destroying some of these mask ROM parts on there. Well, if you look at these parts and analyze them, you might be able to extract that firmware and then transplant that onto a new, say a flash version of that chip and keep that machine running. And that actually happens with surprising regularity. I actually get quite a few of those type of requests. Yes?
We can't see your slides if you're sharing it now or later. Just want to check.
Sure. Okay. So did I lose share screen? Okay, let's try that again. Maybe.
Now,
sure.
Yes, we can see your screen as well. Yeah.
Sure.
Go ahead.
I don't think there was anything. I just want to show the title in case people missed that. So capturing mask ROMs. With that then, so without further ado, thank you. And so, yeah, anyway, so, and then of course, the last thing I think that hits the news a lot, but is not necessarily the main commercial application, is that people just remember some hardware from their youth, maybe some arcade cabinet that they grew up with. And they just want to understand how it works, or maybe they just want to emulate it just to play around with it. So there's also a fair bit of that. And before I go too far into this, I just want to say that really, if you have an easy way to get the firmware out, and easy really means easier, which is a very large class of things, you really should try that first. For example, if it has JTAG or some sort of test interface, and you can just ask it for the firmware to get out, you should really do that. And if that doesn't work, you should try some semi-invasive things. For example, a very common technique is a lot of microcontrollers can read their own flash or non-volatile memory. And so if you can get code execution on it, usually there's some way you can tell it to read its own data out. People like to call this Trojaning it. For a good example of how this would work on a lot of older microcontrollers is they would have a memory map with their external memory adjacent to their internal memory. And if you were able to generate interrupts, say non-maskable interrupts that you could just keep stacking, eventually you can build up so many interrupts that you'll actually overflow all of the memory and sometimes go into external memory. And then if you stop the interrupts and they stop popping the stack, you can basically control the instruction pointer as the stack starts getting popped and execute an external memory and execute your own code. And so that's just one example of how you might get code to execute on a protected device. And there are other ways to do it too. Another way, if all of that fails, you might be able to glitch it. Voltage glitching is something you might hear a lot. things that make the CPU do things they weren't supposed to, or maybe some of the security circuitry. Whatever it is that allows you to get execution or unlock a test interface, just something that allows you to get code out. But if you've tried all that, you've exhausted all of that, or sometimes when brute force just makes sense, this is the talk for you. But if you are thinking about doing this, please consider all these other possibilities before trying this method. And so you might first ask, how is it that you actually get to these physical data structures on a chip? And typically the way that goes is you take a beaker of acid, say nitric acid, like on the left. You will then get a bare die, like the chip in the middle. In this case, it's a deep cracked chip. And then on the right, it's then been put into a microscope and we've generated some high resolution images. Now you can't see it on that image on the right, but that's actually quite high resolution. And if you kept zooming, you actually could see individual metal traces that make up the microchip. Okay, so what's the actual physical layout of these so-called ROMs we keep talking about? And so here's an example. And in this example, what we have is from going left to right, we have these red control lines. And those are essentially the word lines that select which word, that is group of data, we would like to get out of this chip. And then going vertically, we have the bit lines. That is, once we select a word, what is the actual data that flows out of this memory? And the basic idea of it is there are those little black contacts, like vias, that connect basically some power parts of the chip to some of the data parts of the chip. And if you activate one of these word lines, it will select a certain area of one of those rows, and those vias will select which parts of the data get read out as ones and some of them as zeros. But here's the good news. If you didn't quite understand what that meant, we actually don't care about how these chips work for the most part. The only thing that we need to know is, was it in one bit state or another? So for example, if you look at the image on the right, you don't really need to know, that's a real ROM, that's from the Game Boy, for example, the boot ROM. And you can see this pattern where sometimes there's this black circle and sometimes not. We don't need to know anything else about how that electrically works. We just need to be able to tell that there's either a dot or not a dot. And we'll talk a little bit more about how that works and how we can get firmware out. Okay, so you have this chip now. You understand basically what the boot ROM is. You need to be able to do at least some basic imaging to get good enough images to extract the data. And my first piece of advice is, even if you want to image the entire chip, I highly recommend that you do a dedicated imaging to just the mask ROM. And the reason why is sometimes you might have something that artistically looks good for the entire chip, but when you want to get the actual data, you really just want to focus on maybe something that really improves the contrast of just the ROM bits. For example, this is called the contact ROM, and maybe those little circles are going to be perfectly in focus at just the right height, but it might not look good elsewhere on the chip. So you really should do a dedicated imaging run just for that bit of the chip. And then sometimes, depending on the ROM, other illumination techniques may help. And in this case, a contact ROM, cross polarization, which shows surface roughness, oftentimes improves the contrast and makes the images easier to read. So for example, at the top, you see a lot of these black circles on white, but on the bottom, you see a lot more of just white on black. So it's a little bit easier to pick out, especially for computer vision. All right, so now we have some background on what the actual image data might look like. Let's start talking about a tool chain, how you can take this image and actually convert it to a usable binary that you might put into Ghidra, Hydra, or whatever your favorite tool is. So basic tool flow for most of these is you start with an image on the left, you use some program that will give you a high-level abstraction of where the ones and the zeros are in this physical layout, but you don't really know what those ones and zeros mean yet. And that gives you kind of a bitmap. And then from there, you take that bitmap and you do some sort of transform that rearranges those bits and turns them into a usable binary. And so we're going to start by talking about a few tools that do that first step. That is, these three tools can take a microscope image and turn it into kind of a 2D array of ones and zeros. And I should mention, first of all, that if it's a really small ROM, you might not even bother with these sort of tools. If it's just a couple hundred bits, maybe just type it by hand. The most common way I see people doing that is just into a text file using your favorite editor, or sometimes into a spreadsheet. But especially as you get into larger ROMs, you have to ask yourself, do you really want to spend time in a spreadsheet listening to Clippy? No, you don't. You want to grab Clippy up and get rid of him and really just use some of the better tools out there. So one of those tools is Rompar, originally written by Adam Laurie, and it's been significantly improved since his original version. I'm currently the lead maintainer, although most of the work these days are actually done by other people, and I just coordinate the changes there. And it's basically a suite of algorithms that can do things like thresholding to say, hey, is this more white than it is black? And then it'll bucket those two values into either a 1 or a 0. And it's worth mentioning it's written in Python, so if you enjoy Python, this may be your tool that you want to hack on. It has a few features that help it scale up if you're doing some larger projects. One of them is that you can load in a text file, maybe that someone else typed up that is one of these sort of bitmaps. So if you had several people that were collaborating, you actually could load in someone else's data, or maybe if you're working on the same chip, but now with different firmware, you could take your old project in and your old project where you've kind of figured out where physically the bits were, and then load in new data on top of it. The other thing you can do is it allows some annotations in the sense that if you had several data sets that were similar, but maybe had some conflicts and you wanted to figure out who correctly typed it, you can highlight those in the GUI, which allows you to figure out who typed the bit correctly. So that little orange area there, for example, shows a bit that several people disagreed about what the value was. And the last bit is if you load in a new microscope image, you can, but it's same firmware. If you've already done some work to kind of lay out this grid of where all these circles go, but you don't quite know the values yet, you can tell it to kind of move that grid around to align to a new microscope image. And last, there have been a lot of requests for Windows support for this tool. And fortunately, recently, thanks to ClawGrip, there's now an easy Windows setup. You still have to use the command line. There's been some requests for a full GUI flow, but it does mean though that if you just kind of click an executable and go through an installer, you will get a very easy setup. And I will publish the link to that after the talk. The next tool that you might consider using is a tool that Chris Gerlinski talked about last year here at hardwear.io. And this is open source C++. And conceptually, it's similar to Rompar. It's a GUI. It allows you to kind of define these regions where the bits occur and sort of patterns. I would say though, it's more polished, especially when it comes to things like what is the brightness levels and kind of visually showing a histogram, for example, of how much black versus how many white splotches you detected in your image. So in this example image, you can see 2 histogram peaks. And that basically means that one of those is probably the 1 and one of them is a 0. So if you set some thresholds within those histogram values, you should probably correctly classify most of the bits in your image. Another way that you can do this is those 2 tools that we just talked about are good if you have some mask ROMs of up to a size that maybe you personally are willing to kind of sort through the data, maybe manually fix errors. But what if you need to do a really large ROM? Maybe something on the order of 64,000 bits. And for most people, that just gets too tiresome. You just kind of lose your focus, it takes too long. For multiple reasons, you might just find you need some way to scale that up. And that's why the Django-monkeys project was born. And this project was primarily developed by sort of main focus people to basically upscale some of this mask ROM capture efforts for some of their arcade preservation projects. And the way that this was run was they got 5 different people to type up the same bit area, an example on the right there, and then a post-processing script basically did voting to say, hey, did we get maybe 4 out of 5 people that gave the same result on each one of these bits, or maybe at least 3 out of 5? And that allows you to basically assign some probabilities. 5 out of 5 people all agreed it was the same bit value, pretty confident the bit is right. But maybe if only 3 out of 5 said that that was the bit value they thought it was, maybe you flag that for review. And the primary reason to do this was they are very interested in getting very, very accurate results. And in fact, some computer vision results were able to get close on some of the better data sets, close to 99.99% accuracy. So say 1 bit error out of every 10,000 bits. But if you start thinking if you have 64,000 bits, maybe you would have roughly on the order of 6 bit errors. If you wanted it to be reasonably accurate, maybe 0, max 1 bit errors, you need to add another 9. And by having 5 people type up these results, they were able to get close to 100% bit accuracy on these firmwares. And the other main advantage of this is it's a web-based platform. So you just need a web browser, you point your browser there, and people can contribute to these digitization efforts without needing to know a lot about how the software is set up or really what's going on. Just kind of image at left, there's some instructions, and type up the data on the right. It's also worth mentioning to get that set up though, there are a few support pieces. Notably, you have to cut up a source image of a mask ROM into smaller itty bitty ROMs to present to people. And DieToy does that. So if you're interested in setting that up, please check that out. That allows you to slice up mask ROMs. All right, so now at this point, we've presented 3 different tools that allow you to go from a microscope image to kind of a bit array, a 2D array of a high level abstraction of what that firmware held. Now the question is, how do you go from this text file, which just has a string of 1s and 0s, to an actual usable binary? And currently there are 2 primary tools for working with that, and we'll go into those. The first is, well, actually I guess talk a little more about bit order first. So regardless of the tool that you use, you do need to get at least some high level ideas of how you think the bits might be arranged. So anyways, yeah, so as I was mentioning, the previous steps would give you a bitmap. So basically you have this 2D array of an abstraction of what the microscope image had for these 1s and 0s. And now you simplified it into just a text file. You know, where was there a 1 versus a 0? And now you need to take that bitmap, these 1s and these 0s, and you need to convert it into a usable binary. And there's a lot of things that are involved in making that happen. And the first part is you need to figure out the bit order. Where is the high address? Where is the low address? Where's the most significant bit? The least significant bit? What's the polarity? One of the things I glossed over earlier is a lot of times you arbitrarily choose a convention for what you think might be a 1 versus a 0. A lot of times people say, whatever's bright in the image, I'm going to call that a 1, and whatever dark is a 0. But as you start looking at the actual binary, that might not be the case. So how do you start approaching this? Well, the first thing I like to do is look for areas of low entropy in the image, because a lot of times high addresses end up going unused. In the image at the right, for example, you see that there is a dark area on the right where there's really no bit patterns. And that tells us that is most likely the high address of the chip. That is low addresses on the left, high addresses on the right. And that actually narrows down quite a lot of our search space, especially as we may be able to zoom into that boundary region and we might start seeing other things. Maybe, for example, it fills up towards the bottom before it does the top. And that'll also give us some of that per row ordering as well as the column ordering that we see there. And then the next thing you say is, okay, well, we have some rough ideas now. How do we know the binary is correct without going through the whole thing? And at some point you might start saying, let's look for 2 things. Either maybe there are strings in the binary, or maybe it disassembles correctly. And for the first, the strings, a lot of times I find that even if a binary is deeply embedded, it's not too uncommon for there to be a copyright string at the end of it. And so even if you don't expect any strings in the binary, it's not too uncommon to actually find some. So that helps quite a bit. The second is, if you're familiar with the disassembly for this particular architecture, you might find you are able to do some heuristics. For example, for 8051, a lot of times they start with a jump instruction as part of their vector table. Most commonly, this is 02, sometimes 01. And I think you'll find on most embedded architectures, there are similar patterns to look for. The first tool that I'm going to discuss that can do this for you somewhat automatically is Zorro's mask ROM, or Zorrom. And the main advantage of this tool is if you happen to be lucky enough that it supports one of the microchip mask ROMs that you already want to extract, it actually has some algorithms built in for specific chips. So for some of these MCS48, the 8048 architectures, for example, if you just pass in the appropriate architecture flag and give it one of these text files with the bits, it'll automatically decode that to a binary for you. If you want to support your own, it is open source Python. It has kind of a plugin system. And there's an example of what you basically need to add. You just need to add a function that says, given this binary byte offset and the bit index for that byte, just give me the row and the column in the input text file, and it can do all the rest and has a number of add-on tools that can also help you visualize that if necessary. Another alternative program is this program called Bitviewer, and that's written by Chris Gerlinski, and it's designed to be used with Bitract that we talked about earlier. And the main advantage I would say of this one is this one's a little more hacker friendly. If you don't really know anything about the actual physical layout, this has a lot of tools to help you visually swap rows and columns and kind of permute address lines to kind of hack on it until you get something that looks about right. So especially if you just need to do this once and get this to work well, this is a great tool for that sort of workflow. Okay, so at this point now, we have a usable binary. We've started from a microscope image. We've done some conversions to turn that image into some high-level bit arrays. We've taken those bit arrays and we've converted them into a binary by using these transforms. And now we have something we can pop into Ghidra, IDA, or some tool of your choice like that. So at this point, what I'd like to add is that there are some provisions in the Python toolchain, that is the top one. You also can back annotate. That is, if you were to give me a final binary, it's possible to convert that back into one of these 2D text arrays. And then if you had a Rompar project, you actually could annotate that into an actual microscope image. And this is useful if you are comparing some binaries and you're not sure, for example, which microscope image it came from. This allows you to do this sort of checks. Maybe you had a microscope image and you saw several firmware variants, problems like that. All right, and so now some high-level background about how this processing is done. I'm going to talk for the last bit of the talk about how to optimize your microscope images, especially for more modern ROMs like you might find on chips. And in particular, implant ROMs. So the examples earlier were so-called contact ROMs that were really popular when chips first came out. Unfortunately, since maybe the mid-90s or something like that, a different technique called implant ROMs have been used. And the really big thing here is that under a microscope, the small changes in implants, that is doping, that make up these ROMs are not visible typically under a standard microscope. In fact, there is a ROM in that image at the bottom, and other than some dirt that's basically on there, you really can't see any bits or anything like that. It's just basically blank. So the question is, how do we turn this into usable data? And the technique you will see the most to do this is something called staining. And the basic idea is that you take a solution that does some sort of chemical process and shows it differently depending on the doping levels involved. And that image below, for example, on the left, you see the source image, which had no staining. And on the right, we've applied this special chemical solution that shows some bits. And so that can really help to see, like, maybe we could use this on implants because they're basically a type of doping. Except there's a problem. It kind of works, but not very well. And I would say it only really works well on first generation implant ROMs. And so the question is, why does this technique not work reliably? And that's something I spent a long time answering. And for that, we need to look a little bit about the mechanism of how this so-called dash etch, which is one of the more common ways to do this staining to show the dopants, works. And it's basically a mixture of nitric acid, acetic acid, and hydrofluoric acid, everyone's favorite acid. And basically, only the nitric acid and the hydrofluoric acid actively take part in the reaction. And the nitric acid oxidizes silicon, that is, it turns from silicon to silicon dioxide. And then hydrofluoric acid eats away that silicon dioxide that is formed. And these are basically two competing reactions. That is, are we making silicon dioxide faster than we're eating it away? And it turns out that doping concentrations will influence these reaction rates. And there's one other last important thing here, is that if you have any metals in your solution as these acids are working, they're also going to oxidize silicon and interfere with these reaction rates. And that turns out to be really critical. And we'll get back to that a bit. So, so going back, so these, I'm just going to start back here. So these two images are the same ROM. And if you look, you can see that there's actually the same information here. If you look in the upper left-hand corner, you can see, for example, there's a bridge, but it's much clearer on the right image than there's the left image. And so why, despite that these two images are the same ROM, they were prepared with roughly the same dash solution, why are they so drastically different? And one of the big contributions to that is metal contamination. And if you look at that highlighted area on the right that's in yellow, you will see these little tracks. And what those actually are the metal layers that connected the chip together. And if you see this, it means that you had too much metal in your etching solution and it's interfering with your chemistry to show the bits. And there's a couple ways that you can fix this. Is that first, I would say, is if you have a lapping machine, you can actually just physically remove the metal because it's above the actual implant ROM, and just get rid of it physically. And then so by the time you start doing chemistry, there's no metal, no problem. The second thing you can do is you can use higher concentration hydrofluoric acid. It turns out that most people, when they're doing this, they'll use something like Wink, which is, say, roughly a 2% hydrofluoric acid solution. But that tends to eat metal at a much faster rate than does a 20% or a 50% solution. And if you look in failure analysis books, they recommend a 20% solution as a compromise because, safety aside, a 50% solution eats things so quickly that although it does eat the things that you want to eat quicker than a 20% solution, it'll also start to react quicker than you can kind of react. So 20% is a good compromise to get good results. And the last thing you can do is if none of those are a good option, you can occasionally, as you're starting to prepare the chip and eat through layers, you can basically switch to phosphoric acid and eat out metal. And this will eat metal without eating any of the silicon below. And so this can kind of strip that out before it starts to sit in solution and react. Because in most of these cases for the hydrofluoric acid, the metal will actually lift off and could in theory be removed, but it sits in this acid solution for a long time that eventually dissolves. So if you just take some breaks, etch it out, then you will significantly improve your results. Another thing that's kind of a little bit of
John,
weird...
we lost you for the couple of past 10 seconds.
Okay, did you get, okay, so I'll talk about phosphoric acid.
Yep.
So another option is if you don't have polishing machines or you don't want to work or can't get these very high concentration hydrofluoric acid, which is quite dangerous even if you can get it. Another option is you can, as you're etching through these layers to get towards the bottom of the chip, you can use phosphoric acid and etch out the metal from the top layers of the chip. And the reason why you would do this is that unlike hydrofluoric acid, it won't eat the silicon below. And so it'll just eat out those metal contaminations. You wash that off, and then you can go back to hydrofluoric acid etching. Because most of the time the issue is the hydrofluoric acid will etch the, say, silicon dioxide, metal will float to the top, but because it's not removed from the solution, hydrofluoric acid will continue to react with it and then start damaging your chip. Another part of this art to get good images is that there are some other special things you can do to tweak this process to make different doping concentrations easier to differentiate. And one of them is, it turns out that a bright light, I think it has to be halogen, not LED, if you shine that on the chip during this process, it also favors some of these reactions more strongly than others. And generally I found that this level of selectivity is not really required for older chips because the implants are just so much larger. You just don't need to be as careful. But if you have a newer chip with much thinner differences, then you need to do things to enhance this contrast even further. And this definitely works. In this case, for example, it was an RSA secure ID. And I was able to get this to work a little bit without this. But once I started shining a bright light on it, it was night and day. The contrast was so much better. This is fairly clean and you could extract the firmware on the right. But before it was going to be difficult. I would have had to combine, say, multiple images to get something useful. Another really important thing is that you also may get temperature effects. I mentioned that there was acetic acid, which is typically used in dash etch. There's a couple of problems. First is that acetic acid freezes at pretty low temperature, pretty low temperature, high temperature, freezes at pretty high temperature, relatively close to room temperature. And the problem for me was I had a garage that was detached and got very cold in the winter. And so if I didn't put a heater on in there, it actually would crystallize out of solution onto the chip and cause severe problems. And that image to the right, you actually see acetic acid that's been solidified on the die and really destroyed the reaction. The other thing in general too you need to be aware is a lot of these reactions are strongly temperature dependent. So that means that you may have, if you increase the reaction temperature by maybe 10 degrees, the reaction rate may increase quite significantly. So do keep an eye on what temperature you're running things at all times. I typically will run this with a heat gun, forced air over the chip, maybe at around 100, 120 Fahrenheit, because that for me gives a lot more regularity that regardless of the temperature of my lab, it will give some regularity on results. And the other thing that I will do is I will preheat my lab before doing these reactions with a space heater. And I won't actually even attempt these reactions unless the lab is, let's say, at roughly 75 Fahrenheit or higher. For other things, you also need to be really careful because these are very thin structures and you're kind of etching through them as you're doing these competing reactions. It turns out that if you let the acid sit there too long, you'll just shoot all the way through them and you will completely destroy any doping that was there, and it'll just get dissolved and all the information is lost. So in the image to the right, for example, you see that there are bits visible in the upper right-hand corner, but as you go to the lower left-hand corner, no bits are visible. And that's because, or very poor contrast at the very least. And that's because it was etched too long. And at that point, all of the implant was etched through, and at some point it just starts destroying the data. If you let it sit for a very long time, you'll get something to the left, like the left. And that's where this chip has been very much pitted and all of the data has been destroyed. The chip itself is completely destroyed, just not very usable. So you need to very carefully time these reactions. In fact, if you look in failure analysis books for dash etch, the typical recommended time is on the order of about 10 to 15 seconds. So you really need to be careful, really should time this with a stopwatch, and you should really consider being more conservative with your times and do smaller amounts, smaller increments if possible, rather than letting it sit too long. What I might do, for example, if I don't know about a chip, maybe I will do 5 seconds to start with. And in order to do these very short times, you also need to be very careful, like doing things like instead of taking a chip out, which may still have droplets of etchant on it, you need to add a lot of water to that solution to kind of even out the change between etching and not etching. So that was the bulk of the presentation. Thank you for listening. I do have a few backup slides if we want a little more detail, but I think this is probably a good point to stop. Here are some links for the projects I've discussed, and feel free to reach out if you need something. Thank you for listening.
Thank you, John. I hope you have all your fingers with you after you do all the lab tests that you've been playing around with different fluid acids. John, you must have received some questions into your chat window.
Sure. Let me see if I can bring that up. So the screen is a little bit different. Maybe if I stop share, then, okay, then I can get chat. Okay. I cannot see the chat though with the screen sharing. Okay, so let me look through the chips here. It's not that bad if you avoid drinking that. I assume that's referring to the hydrofluoric acid. I think that comment may be facetious, but I will just add just for clarity. Yeah, if you actually spill it on your arm, for example, you can go into cardiac arrest and die. I just got another message that I froze again. Can you still hear me?
Yes, I can hear you.
Okay, yeah, so it's actually you should be really careful with it. And that is the fun fact, that is the difference between a toxin and a poison, if you're not aware. A poison has to be ingested. A toxin is dangerous if you just get skin contact. And that's why hydrofluoric acid is toxic instead of classified as a poison. Extra fingers, yes, eyes, fingers, toes, 2, 10, 11, if anyone knows that reference. What acid did John use earlier in the talk? Nitric acid, okay. More specifically, I would add that I used white fuming nitric acid. There are several grades of nitric acid you can use. Generally speaking, to decap a chip, I would recommend using the strongest grade of nitric acid that you are comfortable using. It will be faster and it will be generally gentler on the chip. The very strongest is red fuming nitric acid, but this is like an abhorrent substance. Like if you look at this thing, It's like if there was an acid hell and the acid came out of acid hell, this is what it would be. It just spews red death. I mean, it'll destroy everything, even physically located near it. It's not very pleasant. You really want to work in a good fume hood. I use white fuming nitric acid, which is not quite as strong, but still quite strong, but doesn't put off these red clouds as much as you work with it. Let's see, safety aside, John's motto. I am not letting my son see this presentation. lots of comments about safety. And HF is very good for cleaning. You know, fun fact, I had some glassware a while back that actually did get very messed up. And I did, in fact, put some hydrofluoric acid in there to clean it out. And I'm sure I lost a little bit of the glassware in this process, but it took all of the gunk right off the glassware. So yes. Interruptions, yes. Cleaning dishes, not just killing you. What type of microscopes do I use for these jobs? What is the smallest scale they can do? How small do modern chip mask ROMs get? Okay, sure, that is a good question. So for a lot of the stuff that I work with, I am using a Olympus BH2 microscope, basically, with either one of two objective sets. In most of the shots that you see, I am using so-called Minotauro M-plan APO objectives, which are long working distance objectives. And a lot of times I work with these older chips with fairly large feature sizes, you know, chips from the 80s, 70s, you know, stuff like that. And these have feature sizes in the maybe the multiple micrometer range most of the time. And so that objective is very well suited to that type of stuff. And the reason why I use that specific objective is it's so-called long working distance. And that means that if I need to have a chip that's still in this package, that means that I can have a large space between the actual die and the objective and still see into the package. If you want to get much higher resolution though, I have a couple other objectives that I can switch to. Notably, I have these so-called Neo S-plan objectives, which the ratings they call the numerical aperture basically determines resolution. The M-plan APO I think is 0.42, and then the Neo S-plan 100X I think is about 0.9. So that's kind of a linear measure of resolution, which is essentially squared for information. So it's quite a lot more information. And then if I need very high resolution, I have oil objectives, which have numerical aperture 1.4. So if you think in terms of resolution increase as you're going down that ladder, it would basically be 1.4 divided by 0.42. That quantity squared would give you a significant increase in actual data over using that 20x objective. So there's a little bit of matching the objective to the task, and then scanning electron microscopes are used if you need something higher resolution, but they're less convenient, so I try to avoid them. So hopefully that answers that.
John, you could take one more question and then we shift you to the discussion room where you will have a lot of people interesting to know how many fingers do you still keep.
Sure. Such experiments, we need sophisticated lab equipment. Any practical example roll products which you performed on these? I'm a little bit careful to discuss chips that I've worked on, but you can look on Twitter. I would say that for most of this, you know, you just need some drain cleaner from the hardware store and a hot plate, and you can kind of do this. Microscope doesn't need to be as fancy as mine, so yeah, I think I can get into more details in the discussion room, but you can definitely use lower end equipment than I'm using. So thank you for listening, and if you have more questions, please join me in the discussion room.
Thank you, John.
All right, bye-bye, thank you.
Bye.